So you're staring at a mountain of raw data. The big question is always, where do you even start? How do you find the actual meaning, the signal hiding in all that noise? Well, the very first step in any kind of data analysis is to compute some summary statistics, to get a feel for the typical values and the overall shape of your data. In this lecture, we're going to dive deep into how NumPy's incredibly powerful and super fast aggregation functions let us turn these giant, complex datasets into clear, simple summaries. Let's get started. Here's our game plan. We'll kick things off with the big idea, what data aggregation actually is. Then, we'll see how to apply it to entire arrays to get that bird's eye view. After that, we'll unlock some much more specific insights using the all-important axis parameter. Then we're going to get into the weeds a bit, looking at some performance and statistical details that really separate the pros from the beginners. And finally, we'll tie it all together with some real-world machine learning examples before we wrap up with the key takeaways. So let's start at the beginning. What in the world is data aggregation? At its heart, it's a really simple idea. It's the process of taking a huge, maybe even overwhelming, collection of numbers and boiling it down to just a few summary values. Think of it like distilling the very essence of your data into key stats that give you immediate, high-level insights. It's your first look before you dive any deeper. Okay, so the core concept here is fundamental. It's all about reducing dimensionality. That sounds a little academic, right? But all it really means is we're taking an array that might have thousands or even millions of elements and collapsing it down into a single meaningful number. A total sum, an average value, or maybe the highest peak in our data. This isn't just about making things simpler. It's about making the data something a human can actually understand. This process is literally the foundation of what we call exploratory data analysis, or EDA, and it lets us grasp the main features of a dataset in just a glance. And of course, NumPy gives us a whole toolkit for this. These functions you see here, they're the building blocks of descriptive statistics. We can find the sum, the mean or average, the absolute minimum and maximum values, and even get into more advanced stats like the standard deviation and variance, which tell us just how spread out our data is. It's all right there for us. Let's start with the most straightforward use case there is, getting that global big picture view of our data by just applying these functions to an entire array all at once. So by default, if you just call a function like data.sum or np.mean, NumPy does something really simple. It conceptually flattens the entire array. Just imagine taking a big multi-layered spreadsheet and lining up every single cell into one long row. That's what NumPy does behind the scenes. Then it just runs the calculation over every single one of those elements. The result? One single number that gives you a global summary of the entire dataset, no matter what its original shape was. This structure is absolutely fundamental in the world of machine learning. A 2D array is the standard way we represent a dataset. You can just think of it like a table. Each row is a single observation, or what we call a sample. That could be a customer, a patient, or a house for sale. And each column is a specific characteristic or feature of that sample. Things like age, income, or square footage. This samples by features matrix is the universal format for feeding data into pretty much any machine learning model you can think of. But here's the thing. A single number for your entire dataset often isn't enough. To get truly useful summaries, we need to go from that global view to something a lot more granular. And the key to unlocking all of that power is the axis parameter. This is a critical concept, and honestly, it's one that trips up a lot of people when they're starting out. The access keyword doesn't tell you the dimension you're getting back. Instead, it specifies the dimension of the array that is going to be collapsed or squished down or aggregated away. The best way to think about it is to ask yourself, which dimension is going to disappear because of this operation? Okay, let's break this down. For a typical 2D array, think of a spreadsheet. If you say axis equals 0, you're telling NumPy to collapse the rows. So imagine moving down the rows within each column to calculate a value. The result is one summary number for each column. Now, the other way around, axis equals 1 means you're collapsing the columns. So you're moving across the columns within each row, which gives you one summary statistic for each row. And this table just perfectly illustrates what happens to the shape of your output. With axis equals none, or if you don't specify it, our 2x3 array collapses into a single number, a scalar. But look what happens when we do specify an axis.
If we aggregate along axis equals 0, we collapse the two rows, and that leaves us with a 1D array of shape 3. See? One summary value for each of the 3 original columns. But if we go along axis equals 1, we collapse the 3 columns, and that leaves us with an array of shape 2, one summary value for each of the 2 original rows.
Let's make this super concrete with a real-world example. Imagine you have a data set of student grades, right? It's a 2D array where the rows are the students and the columns are the different subjects. Now, we can use the axis parameter to ask very specific questions. If we want to find each student's overall average grade, we need to average across their subjects, so we use axis equals 1. But what if we want to find the average score for each subject, maybe to see which class was the hardest? Well, then we need to average down the columns of students, so we use axis equals 0. This is exactly how the axis parameter turns a generic operation into a powerful tool for targeted analysis. All right, now that we've got the basics down, let's go a level deeper. We're going to look at some of the subtle but incredibly important details about performance and statistical accuracy. Honestly, this is the kind of stuff that separates a beginner from an expert.
So a common question is, why not just use Python's built-in sum function? And the answer boils down to one word: performance. It's a huge distinction. Python's sum function is made for Python lists. When you use it on a NumPy array, it has to do this really slow, step-by-step process of creating a Python object for every single number before it can add them up. But NumPy's np.sum, it skips that whole Python layer. It operates directly on the raw C-level data in memory. And that is the secret to its incredible speed. The rule is simple. If you have NumPy data, always use the native NumPy version of the function.
And this chart just drives that point home dramatically. On an array with 1,000,000 elements, Python's sum takes 104 milliseconds. Now look at NumPy's np.sum, 442 microseconds. Let that sink in for a second. That's a mu symbol from microseconds. We're talking about a difference of several orders of magnitude. This isn't a small optimization, it's an absolute game changer that makes large-scale data science in Python even possible. Here's another little nuance for you. np.mean and np.average look like they do the same thing, but they're not quite identical. np-mean will always calculate the standard, plain old arithmetic mean, but np-average gives you the extra flexibility to calculate a weighted average. You can pass it a weights array, which is perfect for scenarios like, say, calculating a final grade, where your homework, quizzes, and final exam all have different weights. Now for a really critical statistical point. By default, NumPy's np.std calculates the standard deviation by dividing by n, the number of elements. And that's totally correct if your data represents the entire population. But in data science, we almost never have the whole population. We're almost always working with a smaller sample. And when you calculate the standard deviation of a sample, it tends to be a little bit too low. It underestimates the true standard deviation of the whole population. To fix this bias, we use something called Bessel's correction, which just means dividing by n-1 instead. You tell NumPy to do this by setting a parameter called DDOF, delta degrees of freedom, to 1. It's a tiny change in the code, but it makes a huge difference for the validity of your statistical conclusions. Okay, so we've covered the theory, the performance hacks, and the statistical details. Let's now see how all of this stuff comes together in the real world, in actual data science and machine learning pipelines. Yeah, the first lesson you learn in data science is that real data is never clean. It is always messy, and it almost always has missing values. In the world of NumPy and pandas, these missing values are represented by a special value, NaN, which just stands for not a number. So here's the problem with NaN values. They're contagious. If you try to run a standard function like np.mean on an array that has even one single NaN in it, the entire result just becomes NaN. The whole calculation is ruined. The solution is to use NumPy's special NaN safe versions of these functions. As you can see, functions like np.nanmean or np.nansum are just designed to gracefully ignore the missing values and do the math only on the valid numbers. In any real-world analysis, these functions aren't just useful, they are absolutely essential. And this slide right here shows a classic machine learning pre-processing step where our axis-wise aggregations are completely indispensable. It's called z-score normalization. A lot of machine learning algorithms just don't perform well when your input features are on wildly different scales. Like, imagine one feature is age in years and another is income in thousands of dollars. The whole goal of normalization is to rescale everything so all features have a common mean of 0 and a standard deviation of 1. And the process, as you can see, is a direct application of what we just learned. First, you calculate the mean and standard deviation for each feature, which means for each column, so you use access equals 0. Then, you just apply the formula to every element. This entire critical process is built directly on top of access-wise aggregations. All right, we have covered a ton of ground, from the basic definitions all the way to the nitty-gritty details of performance and real-world application. So let's just take a moment and pull together everything we've learned. So let's recap the core principles. First, aggregations are our #1 tool for taming data complexity and getting those first crucial insights. Second, when it comes to performance, you always use NumPy's native functions on NumPy arrays. Third, you've got to master the access parameter to go from that big picture view to a more granular one. Remember, access equals 1 is across the rows, access equals 0 is down the columns. Fourth, for good, solid statistical work with samples, remember to use DDOF equals 1 to get that unbiased estimate. And finally, when you're dealing with messy, real-world data, the NaN-safe functions are going to be your best friends.
You know, when it comes down to it, these aggregation functions are so much more than just math operations. They are the tools we use to transform raw, meaningless numbers into actual knowledge, into real insight. They are the very first step in uncovering the stories that are hiding deep inside your data. So the only question left is, what story are you going to find first?